So, final takes. Oh, come on. You can't. Oh, boy. Anyway, okay. I got to look it up because I don't know either. Because, you know, I've got several classes I'm teaching. So, let's just go. Oh, thank you, Gary. Anyhow, okay. Calendar. There we go. Yes, thanks, Gary. But since you've asked the question, May, I'm actually going to go to my calendar and I am going to look at it. Here we go. Let's see. This is, oh, we got Cinco de Mayo coming up. Oh, not the same as previous years, unfortunately. Anyhow, getting over here in the finals week, you guys have your final at 12 o'clock on Wednesday, 13th. Lucky 13, Wednesday. Lucky 13, 12 o'clock. Okay, enough of that stuff. So now let's go to Blackboard. And so will we not meet? Oh, well, let me go back to my calendar. Okay, your last day of class is Friday, May 8th. In other words, that would be a week from today is May 8th. So that'll be your last class meeting. We will have class on Wednesday, the 6th also. Then in the following week, which is finals week, I won't see you on Monday, but I will see you on Wednesday for the final exam. Okay, is that clarifying? Good enough? Yes, okay. So now let's take a look at, I'll put it in student view just to make sure that, oops, why are you not working? There we go. Just to make sure that this is the same thing you're seeing. Okay, the sapling issues, I think, have been resolved. The gentleman over at Sapling, he's very willing to get with anybody that's having trouble getting into Sapling, but he has to know about it. So you won't be able to contact him, but if you let me know that you're having a sapling issue, I can get that information to him, and then he will contact you really quick, and he'll be wanting to set up a Zoom meeting to look at what you're seeing on your screen, and then he will get it fixed for you. So if you have a sapling issue, please email me and send me a text message so I'll look at the email, because I might not look at it for a while. Okay, so if you have a sapling thing, time's running out, so we can't afford to have any dead time because you can't log in. So let me know as soon as it happens, and we'll get that guy on it. Then the next thing is exam 4 will be a week from today. Yay. Exam 4 will be Friday, May 8th. It will cover chapters 5, Thermochem, chapter 6, electronic structure and periodic properties. There'll be a few questions from chapters 1 through 4. Be able to do everything in the presentations for chapters 5 and 6 and everything in the worksheets for chapters 5 and 6. And there might be a few things from sapling. Everybody good? Everybody got it? What's going to happen? Right. So going to sapling. I moved some due dates a little bit. So I didn't move anything at this end. So the topic introductions and the homework for chapter 6 are still on May 2nd. So that's tomorrow evening. Remember, with the topic introductions, you got to finish it on or before the due date, or you will not get any credit. It does not allow for a partial credit. You either get all or nothing. So on or before tomorrow, 1 minute to midnight, you need to finish those up and get and hit the number of points that the target points. The homework, on the other hand, you'll have five more days after the due date to work on it. But deducting points on the questions that you have not done after the due date. So that adds up. If a person waited till the last possible day to do a homework, you would be losing approximately 22% of the points. So you don't want to do that, of course. So you want to try to get it done before the due date, but you could, have a few questions you do the next day, and it would not impact the score too much. So those are due on the 2nd, and you can see the rest of how this thing's progressing. The thing I did, though, was I took the topic introduction for the gas chapter and moved it out the last possible day, which is the same. It's the day before you got guys' exam, because I'm going to need all of the sampling scores in to then put with your final exam grade to get your final grade. So I can't let grades still be coming in from sampling after the final exam. Now, let's see, Chapter 9 homework is due on the 8th. So if we go 9, 10, 11, 12, 13, actually the last day to be working on Chapter 9 homework will be one day after the final exam. Okay, so that's where we're at. Now, on the other hand, if you see that there's just no way you're going to be able to finish these things up, don't just, give up or something. Please tell me. Please send me an email. If things are getting really short, send me a text message so I'll get right on it. And I'll see if there's anything we can do to make that work out. Because it's not my objective for you guys to get a lower grade in this class. Okay? So that's the deal on sapling. Has anybody got a question or a comment there? Okay, I'm not seeing anything, so I'm going to jump out of sharing my screen. And make sure I haven't missed anything in chat. No, it looks like we're good there. And probably a few people have come in since I started things up, so I need to move them into their groups. So give me a moment, and I'll do that. Oh, it says my connection's getting poor. I'm going to turn my camera off. Okay. Well, I just want to say while I'm doing this that I just, I really wish that everyone's family and friends are well in this current situation. But I know with me being in contact with about, it's not quite 75 students, but I don't know, maybe 60 students, the chances of someone having something bad going on is pretty high considering. So I don't want that to happen, and I hope it's not. So okay, so let's see. We're working on a worksheet, but before I do that, let's just go back through the PowerPoint for just a second to make sure we're all good there. And let me see. I'm going to skip down to where it starts talking about Lewis structures. So the rules for doing Lewis structures. Add up all the valence electrons. If it's a polyatomic anion, add 1 electron to that total for each charge on your polyatomic ion. If you have a cation, subtract 1 electron for each positive charge that it has. Then you connect the atoms using single bonds. It takes 2 electrons to make a single bond, so you add up this and subtract them from your total, from the valence. If you still have electrons remaining, you complete the octets of any atoms on the outside of the molecule, unless those atoms happen to be hydrogen, beryllium, or boron, and hydrogen only can have 2, and beryllium can only have 4, and boron can only have 6. But then everything else is supposed to have 8. So if you've got electrons left over, you can put them on those exterior atoms, but in twos. Put 2 on one, 2 on another, 2 on another, and then just keep going until you use them all up. You want to evenly distribute them. Then if you still have electrons left, you put them on the center atom and they become lone pair. And what we'll see in situations where you have an expanded valence, in other words, you can have more than an octet on that center atom, you're going to start having, multiple lone pairs on that center atom, and that's perfectly okay. Then step 5, you check for octets on everything that's supposed to have an octet. If you don't have an octet, then you can take lone pair electrons and roll them over into the bond to make a double bond or a triple bond. Okay? And then, if it happens to be a polyatomic ion instead of a molecule, instead of just a simple molecular compound, put brackets on it, indicates charge, and then you've got the Lewis structure. Okay, so that's the steps. And then we went through some examples. We did carbon tetrachloride, we did silane, we did ammonia, we did water, we did hydrogen fluoride, we did the situation where you didn't have an octet on that carbon in the middle, so then we took a pair of electrons off the oxygen and put them into the bond, creating a double bond, and then now the carbon has an octet. And it did not change the number of electrons the oxygen had, so the oxygen still has an octet. Then we did this example, same kind of thing. First you take a pair from the oxygen, then you take a pair from the nitrogen, until you wind up with a triple bond, and both sides, nitrogen and oxygen, have a lone pair of electrons. We saw this for carbon monoxide, carbon dioxide. Then we saw this weird thing where you have an odd number of electrons, and at that point, you're having to decide where to put that lone electron. And we're going to be getting into how we can figure that out for sure, but we haven't done that yet. Then we did, what's it going to like if you have less than an octet? Well, it's okay if it's beryllium or boron, because beryllium is only supposed to have 4 electrons and boron's only supposed to have 6. Gary, yeah, most electronegative in the middle. No, least electronegative in the middle. There we go. Least electronegative in the middle of the molecule for now. Now, after we get done doing a few more slides, we're going to see that there is another way to figure out what is the most likely structure, but I'm trying to go at that progressively, so we're not going to talk about that quite yet. Then the next slide was expanded valence, so now you've got more than an octet on the center atom. This phosphorus has 10 electrons and the sulfur has 12. And then we did not go any further. On the PowerPoint, we went into a worksheet, which is where I want to go back to. So let's take a look at the worksheet for a second. So it looked like this. It would be really the best thing if at home you print one of these out and you're marking on it, or if you have a digital copy that you can mark on. Depends on your technology of what you got available. If you can't keep a digital copy that you're marking up, then you need to print it if you can, any way possible. Okay. So we last time did carbon monoxide and we did boron trichloride, we're ready to move on to sulfur trioxide, methane, CH4, and phosphorus trihydride, and some of these other ones. Now, to follow along here, I can't keep this displayed and also work through these. So I just thought of this. I need to make sure you guys know where to find that. So let me click onto sharing my screen for a second. Okay, I'm sharing my screen. And to look at that sheet, you need to go to course materials, and then you would go to worksheets, and then you would go down to chemical bonding and molecular geometry, and there it is, molecular geometry lab, although we're doing it in class, and that will give you the worksheet. So you want to keep that open over in Blackboard so you can then refer back to it when we're working through this. Okay, so that's how you have one of those out to look at. And then if you're needing a copy of the periodic table, you can go back to Blackboard, go to course materials. No, not course materials. Just over here on the left, it says periodic table. You click there and you get a periodic table when you're trying to figure out number of valence electrons. So you're going to want those two to be open, periodic table and the lab or the worksheet. Okay, everybody good? Anybody got a question before I stop sharing my screen? Okay, so we're out of there. And then what I'm going to do is I'm going to put up the whiteboard. And the whiteboard is set up to where you guys can write on it. And so I'm going to look at my copy of the worksheet and we'll just move on. So our next compound that we're looking at is sulfur trioxide. So it's going to be SO3. And what I'm going to need for someone to do, and I'll choose somebody using the attendance application. What I'm going to ask you to do is put in the number of valence electrons. So you can write that in right next to the equal, and then draw the Lewis structure below. And then we can debate as to whether it is the right Lewis structure. And I know you guys can Google this, but try to do it, because when you're taking an exam, well, I can't really say that this time. Anyway, you do need to know how to do this. Okay, let me see where we're at with everybody. Okay, everybody is in my attendance app, so I'll just let it pick somebody. Okay, it's saying Erica. So I'll put that in the chat too. Okay, there you go, Erica. Please type in the number of electrons in the valence. Thank you. And then draw the Lewis structure, please. And then I'll check and see if people agree with you. Now, drawing those dots is just a hassle with this thing. I wish there was an easier way. Okay, so now at this point, I will ask, does anybody not agree with the structure that Erica did for us? Well, first off, does anybody not agree with the number of valence electrons? You can just, type it in chat or say, I don't agree or whatever. So everybody's good with 24 electrons. Okay, so for my next question, does anybody disagree with the Lewis structure that she drew? You can chat or say it or whatever if you don't agree. Okay, not hearing anything. So my question would be, oops, wait. Okay, I'm waiting. It wasn't in all caps with an exclamation point, so it's not exactly rude. It's just a request. Missing a few. Oh, so you want those dots there too. Okay, Erica, do you agree with what May did to your picture? I don't think the numbers match the diagram. Oh, sorry about that thing. Wait, what I didn't do any thin. Oh, well, now we're getting wild and crazy. Okay. Too many on sulfur. Okay, well, let's first make sure we got the valence right. So I'll do a little over here. Okay, you got one sulfur, you got 3 oxygens. So if you look at the periodic table and you're going over either sulfur or oxygen because one is right below the other one, you've got 2 electrons in the s orbital, and then you've got 1, 2, 3, 4, let's see. We've got altogether, you've got 6 electrons, valence electrons. You guys agree with that? Anybody disagree? Let me know. So you got 1 times 6, so that would be 6 for the sulfur, and then you've got 3 times 6, or 24, for the oxygen, so you've got 30 electrons, right? Now, if we do bonds between the sulfurs, or between the sulfur and the oxygens, it looks like that, right? It's 2 electrons per bond, so 2 times 3 is going to be 6. And now we're going to be back to 24 if I subtract the 6 from the 30. Then I can put dots 2, 4, 6, oops, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Whoops, did I mess up? I know that's not right. Hang on a second. Let me make sure I'm not.
Can I propose one?
Go for it. Where do you disagree at?
I don't think there should be a double bond here or here. Oops. I don't think there should be a double bond here or here. I think
Right.
there should be should have been more electrons around the sides. So.
But before you do that, don't do that first. First we got to get this guy right, and then we can do all that stuff.
Mm-hmm.
Okay, so let's go there first. So we had 6 electrons for the sulfur, and then we have 3 oxygens. So 3 times 6 is 24. So that's 30. We make the bonds between the sulfurs and the oxygens, and that's 6. And then you got 24 left over. And I think maybe I was counting wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 18. Now that I am really screwing up here somewhere.
No, I think all we needed to do.
Hey,
Yeah.
you know, Erica straightened me out. Thank you. Let's fix that then. Okay. Let's make that right, because what she is saying in the chat is correct. 3 times 6 is 18. I just failed elementary school.
Love that for us.
So we do that, and now this is all going to change, isn't it? Oops, sorry, that's bouncing around. So now we've got 20. Okay, so we do have 24. Yeah, that's right. So we were correct up here earlier. Now then, if we have 24, now let's fix the rest of the math up. Hang on a second. Oh, God, I hate this thing. Why will it not allow me to?
I can write if you'd like me to. I have my pencil.
No, it's not letting me. Okay, let's just do this. I was gonna erase it, but let's just do that. Okay, so now you've got 18, right? Take 6 from 24, you got 18. So now let's do that. We got, let's see, that would basically give us 3 pairs on each oxygen. Everybody good there? And the only problem we have is the sulfur does not have an octet, because the oxygens all have octets. They all have a bond and 3 lone pairs. So the bond is 2, the lone pairs are 2, 3 times 2, 6, 2 more, 8. So the oxygens are okay. But the sulfur only has 6 electrons, has 3 bonds, 2 electrons per bond. So that's going to be 6. So in order to fix it, what do we do?
Add a double.
Yeah. You're right. Yeah. You can add a double bond by taking a pair of electrons from any of those oxygens. It doesn't matter which one you do it from. So I could take that pair and bring them in. Oh, I'll tell you what, let's not do that, because I want to try to match up with the, oh God, I hate this thing. Okay, let's not do this pair. Let's do the pair over here, so that it matches up what we were doing originally. If we do that, whoever made the red marks, could you delete those, please? You click on them with the arrow thing and then hit delete.
Where is delete? Can I just move them?
No. You can just hit the delete key on your keyboard.
Oh, oops. 1 second. I'm on my iPad.
So if you're on an iPad, I have no idea.
There we go.
Okay, now the other 2 red lines, who put those in? Or I don't care who it is, but can you erase them? Those other red lines. No, that's not going in the right direction. You just click on it with the little arrow thing at the top and then hit the delete key. I wish it would let me delete, but it won't let me do it.
We should just paint over it with white.
I suppose, but golly, that's kind of, no, anyway. Yeah, I can do that. Oh, you just did it. Thank you. Okay. So now, if we do that, then what we have, let me get a color. What we have over here is what you will get if we move that pair of electrons. Everybody is seeing that? When we move this pair of electrons right here, we now have this double bond. And so now the sulfur has 8 electrons. I'll mark it up and show you what I mean. You got a pair here, a pair here, a pair here, and a pair here. So that's 8. So now the sulfur has 8 electrons. The oxygens still have 8 electrons. If you don't believe me, we can count these. 1 pair, 2 pair, 3 pair, 4 pair. 4 times 2 is 8. This oxygen has 8 electrons. And the other oxygens we didn't change, so they still have an octet. So like I'm trying to get you guys to do, please use those rules and follow those steps. Don't just jump into it, because you can wind up with like crazy things that just aren't real. Okay, and especially when we get into the expanded valence, it's really easy to come up with a structure that is just not real. Does anybody have a question on how to do this? Could you do this if you had no help, you just did it? I'll let you think about that a second. See if you have a question.
I think it would be beneficial to try one more.
Alrighty, I don't see anybody. I'm going to clear the screen. We're going to go to the next one, which is on the next page here, it looks like, yeah. So the next one's going to be CH4. So I'm going to clear this and put in the formula. And first thing you want to do is, again, figure out the number of valence electrons. And, you know, I hope your math is up to date so that it's better than mine, because I obviously don't know my multiplication tables. But anyway, I'm going to ask somebody to fill in the number of electrons and draw the Lewis structure. I'm going to check to see if we've gained anybody since I was last. Nope, I still got the right number of people. Okay, I'm going to let my attendance app pick somebody. Oh, that's funny. I'm going to skip this person because they've already been answering a lot of stuff. So I'll go to Lily. Hi, Lily. Hope you're doing okay. Would you put in the number of electrons and draw the Lewis structure for us, please? You had me worried there for a minute. I thought you were going to say that it was 0 electrons. Uh-oh, that's not going to work. Thank you. Anybody not agree? I'll do that down here. Does anyone not agree with either the number of electrons or the Lewis structure? Yes, it does. And it does for me most of the time too. When I was in graduate school and I was a graduate student, we had an undergraduate researcher, and our research advisor would, on Saturdays, you'll probably just say this is crazy, but he would make us come in on Saturdays and we would talk about our research every Saturday. This is when I was in grad school. Wasn't that long. I mean, it was a long while ago. But anyway, so this undergraduate guy, he was asked to talk about what he was working on, and he's having him draw on the probably was well, no, it was a whiteboard, draw on a whiteboard his molecule. And he made the molecule as big as the whiteboard. I mean, it was gigantic. And I don't know. Anyway, it was funny. Okay, so nobody's disagreeing with either the number of valence electrons or the structure. Um, the carbon has 8 electrons, has an octet. The hydrogens have 2. Is that correct? Does anybody disagree with the number of electrons they have? Nope, nobody's disagreeing. And you are correct. The the carbon should have 8, and the hydrogens should only have 2. So this structure is correct. Okay, let's move on to our next one then. So our next structure is for pH 3. Sorry about that phone. So the formula is pH 3. Oops. And then number of electrons. Let's see who the phone picks. Jessica. Hi, Jessica. Hope you're doing okay. Would you please draw in the number of valence electrons and what you think the Lewis structure ought to look like? Okay, thank you. Does anybody disagree with either the number of valence electrons, excuse me, or the structure? I'll type it too. Does anyone not agree? Okay, no one is disagreeing. Now I want to point out something here. One of our examples was ammonia. It was NH3. If we're looking at the periodic table, here's nitrogen. Right below that is phosphorus. So since phosphorus is right below nitrogen, it's got the same number of valence electrons as nitrogen. Therefore, the structure for this pH 3 ought to be like the structure for the NH3. So it's going to be the same thing. So some patterns are going to come out of this that you'll notice. But always still go through the rules to get to Lewis structure, just in case, to make sure that you're getting to the right result. Okay, so that is pH 3. Now we're going to go to H2S. So I'm going to erase our screen, put in the formula H2S, number of electrons, and I'll ask somebody to do it. Umu, hi, hope you're doing okay. Please write in the number of valence electrons and draw the Lewis structure for H2S. Okay, thank you. Does anybody disagree with that? Either the number of electrons or the structure?
Would it be slightly polar, like angled?
You're thinking about the geometry, and we've not gotten to that yet. So for Lewis structures, you just draw them on simple, simple. There's no reason to draw it bent, even though we're going to find that the molecular geometry is bent, but we're not there yet.
Okay, sorry.
So I mean, if you did it bent, that's okay. Remember everything's multiple choice anyway. But uh, but anyway, uh, you know, normally you just do something that looks like this. Now I'm going to point out that same thing I did before, and that is you've got oxygen on periodic table, and then right below that you've got sulfur. Right below that you got selenium. So if you did oxygen dihydride or water, its structure would be the same kind of thing. So you can see again, there's a pattern. Center atom is sulfur. It's right below oxygen on the periodic table. Has the same number of valence electrons. Therefore, you're going to get a structure that looks the same, except you got oxygen instead of, or except you got sulfur instead of oxygen for the one we're doing right now. Anybody got a question? Okay, let's go to our next one. And our next one is going to be PCl5, or phosphorus pentachloride. So we're going to start out with number of electrons, and then we'll need a Lewis structure. So let me get somebody here to do that. Evelyn, would you please draw in the number of valence electrons and what you would like the Lewis structure to look like? Sorry, you guys are really going to hate doing these because there's so many dots.
Can I use lines instead of the dots or no?
Uh, yeah, go ahead. Okay, so when you're putting a line in, you are representing 2 electrons. I want to make sure everybody's clear on that. But
Yes.
yeah, that's what, yeah, some people do them that way, and that's okay. So you can do a line instead of 2 dots. Just, just want to make sure everybody understands what they're looking at. That will, that makes it easier. Thank you.
Okay. You're welcome.
Okay, anybody disagree with this? With either the number of valence electrons or the structure? So if you look at each one of those chlorines, they have an octet. Since we're doing these as lines, I guess maybe that makes it easier to see. There's 4 lines, including the bond, for each chlorine. So each one of those lines represents 2 electrons. So 4 times 2 is 8. So each chlorine has 8 electrons. The phosphorus in the middle has 5 lines. So 2 times 5 is 10 electrons. So the phosphorus has an expanded valence, but that's okay because it's a larger atom and it is okay to put that many electrons around it. Anybody got a question? Would it be BXO will connect 3 coins? It would not be a real structure and not one that we'd actually find. But we have not discussed how you would know that. So for now, let's just go with the idea that we want things that look symmetrical. So if you put a bunch of chlorines together, you're going to have a phosphorus over by itself, off away from that, and that molecule is not going to be symmetrical. But some molecules aren't symmetrical really, so then that sort of messes up that idea. But most of the time, if something can be symmetrical, it will be. So, if we're looking at our current example here, this is going to be kind of hard to do, but anyway, you look at that, and that looks the same as that. And then you can do that for every phosphorus chlorine combination. So you end up, you have symmetry, what's called axis of symmetry, or axes of symmetry in there. And if we spin the molecule around the phosphorus in the middle, all the chlorines would be equivalent to each other if you rotate them around. But that's not the reason why this is really the molecule. That will come up when we move on to the next part of things if we haven't quite got there yet. Okay, so, yeah, got it. Hey. Okay, let's go to this one, and things are getting a little more difficult. I'm sorry. Just slightly, not too bad. If you follow the rules, you'll get the answer, so it doesn't really matter. Oops, I don't want to use that color. Let's go back to blue. Okay, SF4. So we got sulfur tetrafluoride. You'll need to get the number of electrons and then the Lewis structure. And if you follow the sequence of the rules, you'll get the right answer. Okay? So let me get somebody from the phone here. Bahata, hope you're doing okay in this current situation that we're all trying to make through. And would you please draw in the number of electrons and draw a Lewis structure for sulfur tetrafluoride? Okay, thank you. So, the lines are representing pairs of electrons. So the fluorines all have 3 lines plus the bond. So that's 4 lines altogether. So 2 times 4 is 8. The sulfur has 4 bonds plus a line. So that's going to be 5 altogether. 5 times 2 is 10 electrons on the sulfur. Does anybody not agree with either the number of electrons or the Lewis structure? Or anybody got a question? Even if you are accepting this is correct, do you have a question? You can type it or say it. Okay, I'm not hearing anything or seeing anything, so we'll go to the next one. Thank you for that one. So this next one is boron trifluor or not boron, bromine trifluoride. So BrF3. This thing is trying to correct what I'm doing, and sometimes it's not getting it right. Anyway, number of electrons. So I'm going to need the number of electrons and then your Lewis structure. And I'll get somebody here. Sam, would you please draw in the number of electrons and what you think the Lewis structure ought to be, please? Uh-oh, I think maybe he has fallen out of here. Yep, he's out of here. Well, let me get someone else. How about Gary? Gary, would you please give us the number of valence electrons and draw what you think the Lewis structure ought to look like? Okay, thank you, Gary. So if we look at this, each one of the fluorines has 3 lines plus a bond. So altogether that's 4. So 4 times 2 is 8. So the fluorines have an octet. The bromine has 2 lines and 3 bonds. So altogether that's 5. 5 times 2 is 10. So does anybody disagree with the number of electrons or the Lewis structure? Or do you have a question about either of those? You only are going to create a double bond if something doesn't have an octet. And so in this case, and you only do that after you've already distributed all your electrons. So first you get all your electrons, on the atom. So remember, first you make bonds, 2 electrons per bond, take that out of the total. You got any electrons left over, put them on the exterior atoms until they all have octets. If you still have any electrons left over, then you put them on the center atom. Then you go back and look and see if something doesn't have an octet that should have an octet. And then in that case, you make a double or a triple bond. So what would have happened here was after you put those electrons on the fluorines, you would have still had 4 electrons left. So you would have put those on the center atom, the bromine, and then you've used up all your electrons. You don't have any left. Then you go looking and see if everything has an octet. The fluorines do have an octet. The bromines got more than an octet, but you can't do any, that's just the way it is. You can't make any changes. You can't move those anywhere or anything. It would not change the number of electrons that the bromine has, and it would actually then cause the fluorines to have too many electrons. Okay, let's go to our next one then, as xenon difluoride. So XeF2 will need the number of valence electrons. And my phone will pick somebody. And it's saying Yareli. I want to make sure that, yep. So Yareli, would you please give us the number of valence electrons and draw the Lewis structure here? Okay, thank you. So if we look at the fluorines, they all have octets. They've got, a bond and 3 lone pairs. The xenon in the middle has more than an octet. It's got 2 bonds and it's got 3 lone pairs. So altogether, that's 5 times 2 is 10. So does anybody either disagree or have a question or anything like that? So I want to go back and summarize something real quick here. If we go back to PCl5, you had a phosphorus in the middle, and then you had 5 bonds. So around the phosphorus, you had 10 electrons. If we then go to SF4, the next one that we did, you got sulfur in the middle, and then you've got 4 bonds, and then you had 1 pair of unpaired electrons, or lone pair electrons. And again, around the sulfur, you got 10 electrons. Or if we go to the next one, the BRF3, there's the bromine. Up, it messed up my B. You had 3 bonds, and then you had 2 lone pairs around the bromine. So you're back to, you got 10 electrons on the center atom. And then we just did this one, and if we're looking at it, the xenon has got 10 electrons. So you can see how these are all sort of related to each other. Same number of electrons around the center atom. It's just we're taking off an atom and adding a lone pair. So for the phosphorus pentachloride, when we went from it to the sulfur tetrafluoride, if we took away this bond to a chlorine and made it a lone pair, then we'd have the SF4. Or for this next one, if we took away, it's a little hard to see the way we're doing it now. But anyway, if you took away one of the bonds, now you'd have 3 bonds and 2 that are lone pair. And then if you took away one more bond, then you'd be left with the 3 lone pairs around the xenon. So these are all related to each other. The geometry around that atom in the middle is going to be constant through all of these, through all, whatever this is, 4 of these. Anybody got a question? This is going to come back when we start getting into the actual shape of these molecules. So I'm going to erase that and put up SF6, or sulfa hexafluoride. Oh, I hit the wrong thing. Here we go. So SF6, number of valence electrons. And we'll get somebody randomly selected. And so it picked Jason. So Jason, hope you're doing okay. I think I forgot to say that to the previous 1 or 2 people, so I hope you guys are doing okay also. But anyway, Jason, hope you're doing okay. And if you would, please draw in the number of valence electrons and what you think the Lewis structure should be. Okay, Jason, thank you very much. Does anybody disagree with either the number of valence electrons or the Lewis structure? Okay, I'm not hearing anything from anybody. So we'll go with that. And we'll go to our next one. And that one is, oops, I'm going to use blue. Iodine pentafluoride. And we'll want to have the number of valence electrons. So, Jesus, hope you're doing okay. And if you would please, draw in our number of valence electrons and what you think the Lewis structure should be for iodine pentafluoride. Okay, I think he's done with this. You notice that each of the fluorines, they, okay. Uh, you notice that each of the fluorines has an octet. It's got a bond and 3 lone pairs, so that's 4 times 2 is 8. The iodine has got 5 bonds, so 2 times 5 is 10 electrons. Now my question is, does anybody not agree with this? or with the number of electrons, valence electrons, or just, a question, even if you do think it's maybe right or whatever. Okay, we're getting 42 valence electrons. Well, let's see. We've got 1 iodine, and we've got 5 fluorines. Okay, iodine's got 7 valence electrons, so does fluorine. So that's going to be 7, and then down here, it's going to be 35. So then, going to be 42. Okay, so let's go with that. So we got 42 valence electrons. Now, we got to have all those fluorines attached to the iodine. So let's see. That's 1, 2, 3, 4, 5. So 5 times 2 is 10. So we're going to have 42 minus 10. It's going to be 32. Stop me if I make a math error. Okay, so let's see. So we'll go with that. So there's 5 bonds. Take away the 10, got 32 left. Then we use those to make the lone pairs. So let's count those. 1, oops, I don't want to do that. I'm going to switch to different color. Switch back to red. Okay, got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13, 14, 15. And so 15 lone pairs, so 15 times 2 is going to be 30. So I've got 2 electrons left over. So Jesus, what do you want to do with that other 2 electrons? You can draw it on there. Make sure he's still here. Okay, he's still here. That's good. You have no idea. Okay, well then let's go back to our rules. We make all the bonds. We use 2 electrons for each bond. We subtract that from the total. So that's when we subtracted the 10. Then the next rule was if you have any electrons left over, you put them on the exterior atoms. So the fluorines were the exteriors. So we put lone pairs on those. That used up 30 of the electrons. Now we have 2 left over. The next rule says put the additional electrons, if you have any, on the center atom. Now, would you like to draw it for me, please? Draw those 2 electrons. Thank you. So now you got a lone pair on iodine. Okay, so now if we count up how many electrons the iodine has, we know when we went around here, it's got 5 bonds. Then we have a lone pair. That would be our 6th set of electrons. So 2 times 6 is going to be 12 electrons. So there's 12 electrons on iodine, which is okay. It can do that. Has anybody got a question on how to get to this point? Okay, you guys are going to want to make sure that you're practicing this because, as you can see, if you're, trying to wing it, you may not be able to. Okay, we'll go to our next one unless there's a question here. I'll give it just a second. So our next one is xenon tetrafluoride. So XeF4, and then again, number of electrons, number of valence electrons. You can see how getting these right really depends on making sure we know number of valence electrons. Okay, let's pick somebody. Erica, would you please draw in the number of valence electrons and what you think the Lewis structure ought to be? Okay. Does anybody, oops, sorry about that. Does anybody have, does anybody disagree with it? The number of electrons, the Lewis structure? Got a question or anything here on our xenon tetrafluoride? Okay, let's go back and look back through these real quick, some of them. So when we did SF6, or sulfur hexafluoride, we had sulfur in the middle, and then we had something like this. So we had 6 bonds around the sulfur, so 2 times 6, 12 electrons around the sulfur. Then we did iodine pentafluoride. So then you had iodine in the middle, and we had 1, 2, 3, 4, 5 bonds going to fluorines, and then there was 1 pair of lone pair electrons on the iodine. So again, you've got 1, 2, 3, 4, 5, 6 pairs of electrons. So 2 times 6 is going to give you 12 around the iodine. And then we did the one we just did. And so here you've got 4 bonds, you've got 2 lone pairs, so that's 6, and then 6 times 2 is 12 electrons around the xenon. So these 3 are, again, related to each other, at least as far as the center atom goes. Okay, what I want to do now, we're gonna do a couple polyatomic ions. We got a carbonate and we've got a nitrate. So let's erase and do those. So you've got CO3 -2. Yep, that doesn't look like a 3. There we go. And then -2. And we're going to need number of valence electrons. Now these are polyatomic ions, so make sure that you get your valence electrons to reflect that they are ions. And I'll get somebody to do this for us. So Jessica, would you please give us the number of valence electrons and then draw your structure for this polyatomic ion, please? Okay. So the oxygens either have 3 pairs. Hey, it's still okay. We all know what you meant. So you got, right. So you got 3 pairs of lone pair electrons and 1 bond on, that's the way it is for 2 of the oxygens. So if we look here or we look over here, there's 3 lone pairs, there's 1 bond, so that's 4. 4 times 2 is 8, So the oxygens, these two oxygens have an octet. We come over to the other side, and you've got two bonds, and you've got two lone pair. Oops, two, not three. So that gives you 4 again, and 4 times 2 is 8. So that oxygen has 8. Then if we look at the carbon here in the middle, it's got double bond and 2 single bonds. So altogether, that's 4 times 2 is going to result in 8, or an octet on the carbon. Does anybody disagree with this or have a comment or a question or something? Yeah, May, what's up? Yeah, May, what you got that you want to talk about? Does the fact that it's polyatomic give it the possibility? Ah, yes. Let's see. Okay, does the fact that it's polyatomic give it the possibility to give more than an octet? No. Polyatomic ion has no bearing on whether it would have an expanded valence or not. It really depends on how big an atom is. Now, Bahada pointed out something, and that is there's no brackets on here. So we need to go back and do that. It'll take me a moment to erase some stuff so it's not so busy. Sorry, guys. Phones are ringing. Almost there. I'm really close. Okay, I got rid of all the stuff. So then, yeah, we do want a set of brackets. So, we do that, and we do that, and we'd say the charge is -2. So we want that on there too. Okay? But thank you for that one. And is there another question or comment or anything? If not, we'll go to the next one. Okay, I'm going to erase that. And our next polyatomic ion is nitrate, NO3, come on, negative. And we're going to need number of electrons, and we're going to need a Lewis structure. So let's see who it picks. As you noticed, it's going around the room again because we've already done it once. May, would you do nitrate for us? Number of electrons and Lewis structure, please. So you've got 5 plus 6 times 3.
Is that right?
Well, what about the negative charge on the ion?
Right, so then +1, right?
Yeah, then you add one more for that.
Oh, that's not what I meant to do.
You can click on it and erase it.
Whoa, what did I just do?
Oh, use the arrow, not the hand.
Oh, gotcha. Ah, okay, sorry. Technical
Mm.
difficulty. So then, did I delete everything?
I'm sorry,
Oh
what's
my
that?
goodness. This is a mess. Do you see everything or did I delete it all?
No, everything's fine.
Oh, it disappeared on my screen. Oh wait, I see it again, sorry.
It's at the
Okay,
top.
so then
Yeah, you scrolled down or something.
it's like not compatible with my iPad. Okay, so then,
Oh, yeah, if you're doing this with an iPad, it would be well, I don't know. If you have an iPad and then you have one of those Apple pens, it might actually be easier.
yeah, it's easier to write, but the formatting of the website itself is weird.
Oh, yeah.
Okay, so this has,
I'm going to add something here at the top just because we really ought to have that.
oops.
There we go. Okay, so okay, thank you. Does anybody not agree with this? So the oxygens, this is, pretty much it's very similar to the one we just did before, the carbonate. You've got two oxygens with single bond, one oxygen for double bond. The ones with the single bonds have three pairs. The one with the double bond has two pairs. All the oxygens have an octet. The nitrogen in the middle has got a double bond, two single bonds. That's four altogether. 4 times 2 is 8. So the nitrogen has an octet. And then she put the brackets on there and the -1. So anybody got a question, disagree, whatever, anything like that? Okay, let's go to this next one. And that is, oops, oxygen difluoride. And we're going to need a number of electrons also. So let's see, it says, yeah, it is repeating around the room. Yareli, you're back up again. Would you please write in the number of valence electrons and what you would like the Lewis structure to look like? Okay, thank you. So the fluorines have a bond and 3 lone pairs, so that's 4 times 2 is 8. The oxygen in the middle has 2 bonds, 2 lone pairs, so that's 4 times 2 is 8. So everything has an octet. Anybody got a question or disagree or anything like that? So now I'm going to do this, and that is if we look at the next one, it's sulfur dichloride. Well, if we're looking at the periodic table, here's oxygen and here's sulfur. They've got the same valence. And then over here, there's fluorine, and then there's chlorine, and they both have the same valence. So that means we got the same number of valence electrons. We got the same ratio between everything. You know, you got 1 oxygen, 2 fluorines, 1 sulfur, 2 chlorines. So the sulfur dichloride is going to look just like the oxygen difluoride. So it's going to be, you know, sulfur, chlorine, another chlorine, dot, 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 and then the chlorines have got the, oops, the 3 pairs. I probably should just use the lines. So it's going to be just like the other molecule. And then if I go back to really early, where we had oops, that's not it. Get the right molecule here. The H2S. Well, that's going to be the same kind of thing too. You're going to have hydrogen to sulfur. The sulfur has 2 pairs, lone pair electrons. And then I pointed out when we did that one that if you consider water, it's going to be the same kind of structure too. And then what we're going to see, you know, when we get into the molecular geometry is that all 4 or 5 of these is going to, they're all going to have the same kind of molecular geometry. They're all going to look real similar. We got 1 minute left. Those last 2 molecules are sort of weird, so I'm going to have to explain some stuff. Oh, Gary, let's see. HS. Oh, I'm sorry. Yeah, you got it. Yeah, let me fix it. Thanks, Gary. I missed that. I was trying to talk and write at the same time. I'm obviously not able to do that. Okay, has anybody got a question? Anything? Okay, not seeing anything. So please do your best to take care of your people, take care of yourself, be safe, and I'll see you guys on Monday. Now, if you need anything over the weekend, please email me, and if you need something right away, also send me a text. And if you have any trouble with sampling, definitely contact me, okay? So otherwise, I'll see you guys on Monday, and you take care. We'll be, it's a good question, Gary. I don't know, but we'll see what happens, okay? I don't know. Thanks, Evelyn.